All right, continuing here in Unit 1, Chapter 6, we're just going over some practice problems. And a lot of these are basically dealing with the idea of adding, subtracting things to mean and median, standard deviation, range, things like that. And so far we're going to start getting into some normal model problems and figuring out with z-scores and things like that is where we're heading. If I'm moving too fast, I apologize, but you're going to have to pause the video because as it is, there's a lot of videos, a lot of problems and stats, so a lot of times you're going to have to pause these just to kind of write everything down that you need to as we go, as well as my summaries along the way of what's happening. But it says here the Virginia Cooperative Extension reports that the mean weight of some Angus steers is 1,152 pounds. And then it says, suppose that the weights of all such animals can be described by normal models. Right away, I'm going boom, bell-shaped curves, it's symmetric, with standard deviation of 84. How many standard deviations from the mean would a steer weigh 1,000 pounds be? And then, which would be more useful, a steer weighing 1,000 pounds or one weighing 1,250 pounds? So, normal model, right? Well, to give you some practice here, there's faster ways to kind of plug this stuff in on your calculator. Okay, you could just plug this all in one step, but I want you to get some practice making them as z-scores. So, point is, if you know it's 1,000 pounds, boom, mean, boom, standard deviation, boom, and they're assuming that we're talking about the entire population. This could be the entire population of their farm, where they're at, okay, which would then make it an entire population. It might not be the population of every Angus steer in existence, but point is, when you plug those in and divide, that's what you end up getting, right? So how many standard deviations from the mean would a steer weigh? There you go, taken care of, right? So a steer would weigh about 1.8 on standard deviations below the mean. Then it says, which would be more unusual, a steer weighing that or one weighing 1,250 pounds? Well, we would set up 1,250 minus. So when you do that, you would do 1,250 minus 1,152, then divided by the 84, and you get roughly 1.17. So this, right here, this one, is further from 0 than this, which we said was 1.17-ish. So because this is farther away, this is more unusual than the 1,250 pound steer. Taking a look at this one. All right, so it's recorded of speeds of cars driving past his house. So this dude, John, is recording speeds past his house, where the speed limit read 20 miles per hour. The mean of 100 readings was 23.84 miles per hour, with a standard deviation of 3.56. He actually recorded every car for a 2-month period. These are 100 representative readings, every car. So, how many standard deviations from the mean would a car going under the speed limit be? So under that speed limit, and which would be more useful, a car traveling 34, or sorry, which would be more unusual? So, a car going the speed limit of 20 would be, if I plug that in, right? So negative 1.08 below the mean. So it says, how many standard deviations from the mean would a car going under the speed limit be? All right. Well, it says the speed limit is 20, all right, and that's the mean of what they were going. So even if they were going the speed limit, the actual speed limit, right, it would be negative 1.08 below the mean that we found when we were doing it. So a car going that speed would be 1.08 standard deviations below the mean. So how many standard deviations from the mean would a car going under the speed limit? It would be farther out than that if it was going under the speed limit. So even farther out than what that is. That's basically your mark. That and farther down. Then it says, which would be more unusual, a car going 34 or 10. So 10, if I plug it in, 10 minus that divided by that, it's negative 3.89. All right. And then a car going 34 miles per hour would be 34 minus that divided by 3.56. It's 2.85. All right, both of which are unusual. So think about it. I said anything between negative 2 and 2 would be a usual score. All right, but this is more unusual. This is even 3, right? This is past 3 standard deviations, which means it's past 99.7% of all data. So it's even farther out there. All right, so then you would go with the 10 miles per hour is more unusual. Going back to that cattle example that we just did, where we know the mean is 1152 and the standard deviation is 84, cattle buyers hope that Angus steers will weigh at least 1,000 pounds. All right, to see how much over or under that goal the cattle are, we would subtract 1,000 pounds from all the weights. What would be the new mean and the new standard deviation? Well, if you subtract 1,000 pounds from everything, right? Remember what changes when you add or subtract from everything. Okay, so things to remember. And suppose such cattle sell at an auction for 40 cents a pound, find the mean and standard deviation sales price. So now I'm multiplying each pound by 40 cents. So now everything changes. So this thing's to remember. So point being here is, if they're doing this, the Angus steers will weigh at least 1,000 pounds. So to see how much over or under that goal the cattle are, we would subtract 1,000 pounds from our weight. So that's why we subtract that to find out our new mean. The standard deviation would not be affected by subtracting. Remember, when you add or subtract, your ranges, your variations don't change. So that stays the same. It's still 84 pounds. Okay? But when you're talking about the sales price, you take that amount of pounds times the 40 cents. That's what that is, but I also must change my standard deviation as well when doing that, because variations change when you are multiplying. Back to the car example. All right, so same idea, same 23.84 miles per hour mean with a 3.56 standard deviation. To see how many cars are speeding, John subtracts the 20 mile per hour from all the speeds, because that's the speed limit. So now it says, what is the mean speed now? Well, if you're subtracting, again, you're not affecting the variation. So I'm affecting the mean, but I'm not affecting my standard deviation. And his friend Berlin wants to study the speeds. So John converts all the original miles per hour readings to kilometers. So if you're going to either multiply or divide, and it says by multiplying by that. If you're going to multiply everything, that means even the standard deviation will change. The point is, I subtract, that changes my mean, but it's not going to change my standard deviation with this. And then it says the mean speed, though, I multiply, so that changes as well as my standard deviation. Because my units are basically changing, I'm going to have to change both of them by multiplying by it. Taking a look at the cattle again, suppose that the auctioneer in exercise 19 sold a herd of cattle whose minimum weight was 980 pounds. Its minimum weight, its median weight is 1140. Standard deviation is 84 still. The interquartile range is 102, and they sold for 40 cents a pound, and the auctioneer took a $20 commission on each animal. And for example, a steer weighing 1,100 pounds would net the owner the 0.4, but then I also have to subtract 20 from it to get that. It says find the min, the median, the standard deviation, and the interquartile range. Now remember, when you multiply, you're affecting everything. When you subtract, you're only affecting the mean and the median, but not the variation. So the point is, we start by taking the items and multiplying them. So to find, it says find all the new mins, the medians. So this, you take the min and you multiply it by 0.4. The median, you multiply it by 0.4. The standard deviation, you multiply it by 0.4. All right. Interquartile range, you multiply it by 0.4. However, I only subtract 20, because when you add or subtract from the actual point itself, the minimum and the median value, but not my ranges. So we do this, all right, to figure out what happens. My new min, it affects both. My standard deviation, I only multiply, right? My median, I do both. And my interquartile range, I only multiply, which is what I was saying before. Suppose police set up a radar surveillance on that street that we were talking about, and they handed out a large number of tickets to speedsters going a mean of 28 miles per hour. So if they were going 28 miles per hour with a standard deviation of 2.4, that's what they found when they were starting to give people tickets. Some people might have been going faster than that, but normally that was on average when they were giving people tickets with a standard deviation of 2.4 miles per hour. a maximum of 33 miles per hour was made. An interquartile range of 3.2 is there. Local law prescribes fines of $100 plus $10 per mile. Now that word per mile, all right, and here's the example of owners per hour over the 20 mile per hour mark. So for example, a driver convicted of going 25 would be fined the 100 base, but they went 5 over. So 5 over times the 10. So it says find the new mean max standard deviation. Again, I'm multiplying the mean, I'm multiplying the max, I'm multiplying the standard deviation, I'm multiplying the interquartile range, but I'm only multiplying the number over, all right, is what we're basically doing. I'm taking the amount over. They went 25, the speed limit was 5, so you're actually taking that minus 20. So this should actually read x minus 20 inside of there is how you're getting that number. And then I'm adding only to the mean and the max, but not the standard deviation or quartile range. So the point is, that's what they're doing here. The mean was 28, so it's 28 minus the speed limit times 10, and then add 100. The max would be the same, 33 minus 20 times the 10, because the 10 is the multiplier, but then add it. But notice how I'm not adding anything here. Okay, the standard deviation, that's not going to change. All right, it says here that the standard deviation was 2.4. I'm not subtracting it from the miles per hour. I'm not subtracting that either. The 3.2 for the quartile range by miles per hour. So there we end up with our new, in terms of dollars, how much they're paying standard deviation and interquartile range. I don't want to race through the problem here, so when I come back, we'll take a look at this next example.